Demonstration problem. Ruslan pushes a 64.4 pound crate with an acceleration of 2 feet per second over a horizontal surface for a distance of 10 feet by exerting a constant horizontal force of 30 pounds, while being opposed by a constant frictional force. Part A. How much work did Ruslan do on the crate? The givens. The magnitude of the weight force is 64.4 pounds. The acceleration, which is along the x-axis, is 2 feet per second. Since this is a level floor, the crate is moving neither upwards nor downwards. Therefore, the crate is at rest vertically, and its acceleration along the y-axis is 0. The magnitude of the pulling force by Ruslan is 30 pounds. The displacement magnitude is 10 feet. To draw our force diagram, we draw the force vectors on the body that the forces are on, which is the crate. At the point of application, the pulling force touches the crate here, the normal force touches the crate here, so the tip of the arrow is at the point of application. The sliding friction force or kinetic friction force acts between the bottom of the crate and the floor that it is sitting on. The displacement we put off and away from the crate, since it is not a force. The final step for our force diagram is to collapse the crate to a particle at its center of gravity and make all the forces concurrent on that particle. This is depicted here. The pulling force is this way, the frictional force is this way. Since there is an acceleration in the positive x-axis direction, the net force must be in the same direction. Therefore, we know that the magnitude of the pulling force is greater than that of the frictional force, and we make this vector longer in length. However, along the y-axis, the velocity is constant. The box is at rest along the y-axis. Its acceleration along the y-axis is 0, and all the forces are balanced along the y-axis. Therefore, the magnitude of the weight force is the same as the magnitude of the normal force. The unknown. What is the work done by Ruslan? Ruslan exerts the pulling force F sub P. So we need to know the work by F sub P. The equation. The work for a constant force is the magnitude of the force, where only the part of the force in the direction of the displacement does any work, times the magnitude of the displacement. Since this is a horizontal force, all of the pulling force goes into doing work. The way you solve work problems is you use Newton's laws to find the force, and you use the equations of motion to find the displacement. To solve for the work by Ruslan or the work by the pulling force, we see that we know that the pulling force is 30 pounds, and we see that the magnitude of the displacement is 10 feet. So this work is simply 30 pounds times 10 feet, or 300 pounds times feet. This was very easy. We now proceed to question B. The unknown for part B is how much work did the frictional force do on the crate? Since we're once again asked for work, we once again write down the equation for the work by a constant force. The work by the frictional force is the magnitude of the frictional force times the displacement. We know the displacement is 10 feet, just like it was before. We do not know the frictional force. Therefore, we will have to use Newton's second law to solve for that. We know that it's the second law and not the first law because along the x-axis there is an acceleration. Since the acceleration is 2 feet per second, the forces are not balanced, and we cannot use Newton's first law. We must use the second law. Looking at the force diagram, we know that the normal force has 0 x component, and likewise the weight force has 0 x component. Therefore, in writing the second law along the x-axis, the net force along the x-axis will not include the normal force nor the weight force. So we write that the net force along the x-axis is the pulling force, that's a positive force, minus the frictional force. Frictional force is in the negative x-axis direction. The other side of the equation is mass times acceleration. So the mass of the crate, because that's the body that the forces are on, times the acceleration along the x-axis. To find the mass of the crate, we use the formula that the weight force is mass times the acceleration of gravity. We substitute in for the weight force 64.4 pounds. For mg, we write m, that's what we want to find, times the acceleration of gravity, or 32.2 feet per second at sea level. Solving, we get that the mass is 64 pounds divided by 32.2 feet per second, or 2 slugs. We substitute in 2 slugs for the mass. Solving for the frictional force, we substitute in the 30 pounds for the pulling force, minus F sub F, the frictional force, is 2 slugs times 2 feet per second. That's 4 pounds, because F is ma tells us that a pound is a slug times a foot per second. This gives us that the magnitude of the frictional force is 26 pounds. We are now ready to solve for the work by the frictional force. Note that the frictional force is opposite the direction of the displacement. For part A, we use the formula that work is the force times the displacement. This formula, however, only holds when the force is along the direction of the displacement. We need a more generalized formula when that's not the case, such as here. The formula for work becomes work is the magnitude of the force times the magnitude of the displacement times a cosine of theta, where theta is the angle between the force doing the work and the displacement vector. Note here that theta is 180 degrees, since the displacement is along the positive x-axis and the force of friction vector acts along the negative x-axis. Substitute. First of all, symbolically, we want the work by the frictional force, so we write magnitude of the frictional force times magnitude of the displacement times a cosine of theta. Substituting in numbers, we get 26 pounds, which we found using the second law for the magnitude of the frictional force, times 10 feet, given as the magnitude of the displacement, times a cosine of 180 degrees. This gives us 260 pound-feet times the cosine of 180 degrees, which is minus 1, or the work by the frictional force is a negative 260 pounds times feet, since the frictional force is opposite the direction of the displacement. Part C, how much work did the weight force exerted by the earth on the cart do on the crate? How much work did the normal force exerted by the floor on the crate do on the crate? So the unknown is the work by the weight force. Since the weight force is not in the direction of the displacement, the equation for this is the work by the weight force is the magnitude of the weight force times the magnitude of the displacement times the cosine of theta. But we notice that the angle theta between the weight force and the displacement is 90 degrees, and the cosine of 90 degrees is 0. So we don't really have to worry about substituting in for the weight force or the displacement. Regardless of what they are, the work done by the force is 0. In general, anytime a force is perpendicular to the displacement, that force does no work at all, since only the component of the force in the direction of the displacement does any work. That completes this excellent adventure.